memory constraints. So with that in mind, there exists a whole other field of theoretical computer studies computational complexity, how complex computation is, either scaling with respect to time, with respect to memory, and even generally talks about how problems scale in terms of difficulty based on the dimensionality of the problem itself. And with respect to that, there are certain computational classes that some of you might have heard of, like P, NP, NP hard. So P stands for polynomial, NP is non-polynomial, so NP, NP. I'm not going too much into the details of these. You can read up on them on your own. But these are the general complexity classes that people look at when trying to group problems in computation. And as it stands right now, even the world's best super IBM can't even solve NP hard problems. So there's a huge number of problems out there that we haven't even discovered yet that can't even be solved by the best supercomputers. And in this kind of, researchers, not just now, since the 80s and the 90s, have already noticed the possibility of a more efficient compute using these so-called quantum computers for certain classes of problems. They're not saying it's a one-size-fits-all solution, but there are certain important to the industries that can be solved a little better with quantum computers, and we'll see what these are in a little bit. But before we go ahead, I just want to show you a slide, which is a picture of the IBM Q's quantum computer. This is one of their quantum computers. I think they have a 20 computer, and I think their highest is 53 so far. So if you look at this, it's a very complicated setup. Most of it, if you see here, the surrounding part, the gold pieces, all of this makes up the cryogenic system, which keeps the chip at a temperature of around 50 millikelvin, which is colder than outer space and cold enough that most atoms and molecules at this temperature don't even move much. And this is the kind of cryogenic setup that they have to use. So they use multiple stages, and they have multiple microwave electronic setups over here, which you can see the wire. And the chip is somewhere in the middle here. After all of this cooling down and after all of this setup, this is where the chip lies, and this is like the core of the quantum computer itself. And again, we'll get into the details of the hardware and how it works in the next session. But I just wanted to show you this to, give you guys an idea of how a quantum computer actually is and what it takes to perform a quantum computation of sorts. So this is both scary and beautiful. Most beautiful things are scary, but this is beauty in complexity, as I'd say. But why quantum computers? We've got computers that can solve most of the problems. Most of us might not have even heard of the problems that aren't solvable yet. Why do we need quantum computers? And there's multiple reasons. So one of the reasons is that Moore's law, which a lot of people are familiar with. Moore's law says that the number of transistors on a computer chip doubles almost every 2 years. And the size grows smaller and smaller and smaller. And it's reached a point where you've got chips that are all at the range of nano. And at this particular size, you're getting so close to something called the quantum limit, which is basically when it breaks down, because the smaller it goes, the more likely it is to start getting affected by quantum effects. Quantum effects, as we know, are only seen, as far as we know, mostly in microscopic systems. So the smaller and smaller we go, the more we enter this microscopic regime, the more the approximations that we take for our classical computers start to fail. And to deal with this, it's more sensible to use a device that in itself system that obeys the laws of quantum mechanics, so that it can be brought to the smallest possible size and can be operated efficiently. So the quantum computer seems to be the more logical approach to this, the breakdown of Moore's law at least. There are a couple of other approaches with phonics and stuff like that you can read about, but this is one of the motivations behind quantum computing. As I had said, quantum algorithms, certain algorithms like the prime factorization and discrete logarithm algorithm by Peter Shor, and the Grover search algorithm are some of the examples of algorithms that are computationally hard problems than your conventional classical algorithms. And this field is so interdisciplinary. It causes, just by trying to build a quantum computer, as I showed you before, it's such a complex device that in the process of trying to build one, you're improving areas of tech. you're improving tech in communication systems, laser technology, optics, photonics, AI itself, cryogenics. So many different fields are involved in this, and each of them undergoes its own sort of advancement through this pursuit of bringing into play actual work. And last but not least, this is a quote I've mentioned by Richard Feynman, which talks about how the simulation of quantum systems not really possible to achieve, at least in this current day and age, using computers we have, because classical systems just not natural to try and simulate a quantum system using a classical computer, right? It makes a little more sense to try and use a quantum computer, something that in its own nature is quantum, to try and simulate a quantum system. And this was actually one of the key quotes by Richard Feynman, along with a paper that he published and by earlier scientists as well, that sparked the quantum information era that goes on to this day. So what makes computation quantum exactly? What is it that is so different about it that differentiates it from every other kind of computing? Qubits are the basic processing unit of quantum computers and quantum communications as well. As you can see, there are a couple of equations and diagrams. There's a sphere that I've drawn that I've put here, and there is this general equation. So I won't get too mathematical here. So I'll just give you a general idea of what these are. This represents the state of this qubit. So the qubit, as you can see, you might recognize the 0 and 1 as something familiar, something similar to a classical bit. Classical bits are always binary. They can exist in 0 or 1. And this sphere is a sort of representation of every possible state that a quantum bit or a qubit can take. And the surface of the sphere, everyone knows that two-dimensional or even three-dimensional shapes have an infinite number of points that make them. And each sphere has an infinite number of points, and each point represents a possible state that this qubit can take. So if you look at parameterization, if you want to look for a more technical term, because you've got this 0 state and 1 state, and this qubit is basically a linear superposition of this 0 state and 1 state. I'll go into a little more detail in this next slide, but before that, let me just say that this 0 state and 1 state is parameterized by these two parameters, theta and phi. And since theta and phi take angles, theta goes from 0 to 180 and phi goes from 0 to 360, they can be represented pretty accurately using this sphere, which is often called a Bloch sphere, BLOCH. So quantum bits are, let me tell you a little more about them. So they're essentially, two-state quantum systems, for a more technical term to it. And as a quantum system, they exhibit these two very key quantum phenomena, which are superposition and entanglement. Again, buzzwords that you all might have heard of. So essentially, superposition states that you can keep the qubit either in the 0 state or the 1 state, just like it. And this notation of angular brackets is actually called the Dirac notation, for those of you who want to remember it. And different from the classical bit is the fact that a qubit can exist not only in the 0 and 1 state, but also in an infinite possible superposition states of these 0 and 1 states, as I showed you before. Can exist in a sum of 0 and 1 states with particular coefficients. And unlike classical bits, they can do this. And unlike analog signals, can exist also in infinite possible values. The only difference is that when you measure them, there is this sort of a measurement called a projective measurement that happens. And essentially what it does is it will always collapse this state to either a 0 or a 1, to either of the basis states. And you can choose this basis, the 0 and 1, depending on what kind of measurement hardware you use. Again, let's not get too much into that, but do remember that unlike classical bits, it can exist in infinite superpositions, and unlike analog signals, which are basically voltages and whatnot, it can exist when measured only, it goes to only the 0 and 1 state, which is why it's called quantum. It's quantized in that sense. Now, entanglement, I've kept this as a separate slide because it's something that's been prone to a lot of large misconceptions. And let me just try to clear these up. It's been called spooky action at a distance by Einstein himself, because he was not very comfortable with this concept of entanglement. And let me try to explain why. So it's not seen as a phenomenon in any other classical theory. It's endemic to only quantum theory. It basically states that when multiple qubits or particles, quantum particles, are entangled, their states cannot be described independent of each other. They cannot be written as a separate vector. And we will see further how to represent such states then. Basically, their behavior is highly correlated. Their behavior remains highly correlated even if you separate them miles apart from each other. And people have demonstrated this many times, even using satellites to communicate using entanglement, which is absolutely mind-blowing if you ask me, because in a day and age where we're able to employ communication systems based on quantum mechanical properties. And it's also very useful, of course, to quantum computing and quantum algorithms. One such algorithm being quantum teleportation, which again, might have heard of. Again, there are a lot of misconceptions about it, but quantum teleportation is where you transfer the state of one qubit to another, sort of like a cut and paste. But there are also ancillary qubits that are used for this. So it's a particular protocol that you have to follow to do this accurately. And it's also used, as I said, in a couple of communication protocols, and also in something called QKD, which is quantum key remarkable encryptions using a quantum system, using the property of entanglement of a quantum system. And by the way, stuff like quantum communications and quantum key, they're already a reality, unlike a quantum computer, which is still facing a lot of challenges like noise mitigation and decoherence. There are actual qubits and quantum communication satellites that are already available, and they are a reality, and it's an active area of research right now. And I urge all of you to go look it up, because it's an absolutely wonderful concept, and it's really beautifully implemented using single photon sources and such. I'll not get too much into that. So I promised that I wouldn't give you too much of a mathematical, if you want to call them states. They're the standard basis states, but we can also have other states like plus and minus as shown. They're also linear superpositions, but individually you can also express states as linear sub of this plus and the minus states. And by the way, whatever is in the angular bracket, they're just to name the states. They don't have any, significance in terms of, except for like why we name them. That is because, bits are 0 and 1. So we want to stay true to that kind of a notation. So 0 state and 1 state, but they don't actually represent a mathematical 0 or a 1 in any case. It's just to name them. And same goes for the plus and the minus. Now, as might, any state psi as a superposition of these basis states. So we'll be sticking to 0 and 1 for the rest of the presentation. So these alpha and beta are the coefficients. And as we saw in the block sphere notation that we had used, we saw cos theta by 2 and pi sine theta by 2. This alpha and beta are essentially the same thing, except that we're generalizing and saying that over there, the phi, the e power j phi term was more of a relative phase between the two things, whereas here, they are generally complex numbers and, unit vectors in a complex space, because you can write this alpha and beta as some vector. You can write them as a two-dimensional vector, alpha, beta within brackets. It is a vector in a complex space. And coefficients then can be done without collapsing the state via measurement. You don't need to measure them, collapse them, and then make another state. You can do a linear transformation, since they're vectors, and change the state like 0, 1, 0, 0, 1, 1. Accordingly, you represent them as each permutation of n-bit strings, and each of them represents a different basis state. So when we have two or more qubits, it becomes 0, 0, 0, 1, 1, 0, and 1, 1. When we have more, you start looking at each of the two combinations of bit strings that are possible, and each of them has a corresponding coefficient alpha I. And this is sort of the starting point from in quantum computing itself, since each n-bit system has 2 power n basis states with just as many complex coefficients side by side. And each complex coefficient represents the probability of getting that state when measured. So when you measure, each bit is measured with a probability of mod alpha I square. This is a fundamental law of quantum mechanics. that state in a linear superposition, each coefficient mod square represents the probability of measuring that state. So when it collapses to either of the basis states, if it collapses to say 110, the coefficient next to 110 will tell you how many times it will collapse to 110 if you have multiple copies of the same state and you measure each time. If that's clear, then we can move on. We can say that in a sense, we can parallelly operate with all of the strings. Instead of a classical computer where you have to query with each string one at a time for a particular register that stores these bits, you have to query each time. Instead, you can see all of these strings and increase the amplitude of the state that we desire. So if we increase the amplitude to a point where the amplitudes of a very small magnitude and the amplitude of the string of bits that we want to measure is increased to the point where it's almost 100% probability that you're going to measure it, it parallelizes your entire process and it makes your algorithms that much faster. And that is exactly what is employed in every quantum algorithm that you will see. So how do you manipulate these states? You have binary gates. Let's move on to gates. So gates are AND gates, OR gates, XOR gates that you guys are familiar with. In this case, we have quantum gates. Not quantum state to that particular basis state. Everything else can be converted. And this is completely physically possible, right? So this makes things a lot more interesting when you're trying to achieve certain target states. So you can, if you want to achieve a certain target state and you have a state that you want to achieve, all you have to do is reverse the algorithm and you will get it. This is not possible with AND gates, OR gates, or XOR gates, where there is some loss of information, 1.0 versus a 0.0. You're losing out on the value of 1 or 0 you're initially using because both of them lead to a 0 in the end. However, in the can be reversed. So you will always have that semblance of information with you. So we generally deal with qubit gates and quantum gates as multi-qubit gates. So single qubit gates, some of them are X, Y, Z, and Hadamard. And these are the most basic single qubit gates that we use. I'll just go through the transformations here. So an X gate would transform alpha 0 plus beta 1 to a beta 0 plus alpha 1. It's just switching the coefficients from 1 to the Y gate would move it from alpha 0 to plus beta 1 to I beta 0 minus I alpha 1, sort of, giving a complex, some phase component to it, right? And Z gate or Z gate transforms alpha 0 plus beta 1 to alpha 0 minus beta 1. So it's when you're trying to, so when you have a superposition, generally you talk about in waves, you have something called interference, where you add 2 in superposition and certain amplitudes that they have are positive, certain are negative. The positive and negative cancel out. So here you want to interfere 2 states such that an amplitude cancels out. You tend to use the Z gate so that it pushes it to a negative value. And when you add the 2 states in some sort of interference, I'll not get into the details of that, you can induce an interference to occur. Lastly, there's the Hadamard gate, which alpha 0 plus beta 1 to alpha plus beta minus. So it changes it to this generalized form that I've written here. It changes it from alpha 0 plus beta 1, beta by root 2, 0, plus alpha minus beta by root 2, 1. All good? So it's very basic operations. They're essentially linear transformations that you're applying to vectors here. Now let's move on to multi-qubit gates, which are, slightly different in that you deal with them separately because you can't necessarily separate out multi-qubit gates and decompose them into multiple. They're inseparable. They will always be dealt with as a single entity. And one of the most important of those is the C0 gate. The C0 gate is the controlled NOT gate. And this gate takes one qubit as a target and the other qubit as a control, right? So if you have 2 qubits, you have one target. The target is what you're acting on. It performs an X gate, which is you're flipping the alpha and beta 0 to 1 and 1 to 0. So if you have a 0 and you perform an X gate to it, you'll get a 1, right? So if you perform an X gate conditional on the second qubit, right, which is the control. So, okay, in this case, I've written down that the second qubit is the target and the first is a control. So if the control is a 0, the second qubit is not flipped, the target is not flipped. Whereas if the control is 1, the target is flipped. And I've written down the transformation here as well. right? The qubit 1 is target. This is what happens. You have this flip from 1 0 1 1 to 1 1 1 0. Whereas if qubit 2 is the target, you have 0 1 1 1 to 1 1 0. All right. So we can use this gate very well. It's called the entangling gate because you can use it to create entangled states, right? So this X surrounded by a circle symbol that I've written here is a product because you write X as a product symbol, and it's used to indicate a combination of two individual qubits into a single set of basis states. So you have 0 and 1 as your basis states here, and 0 and 1 as your basis states here as well. And they're independent systems, but when you want to treat them as a single entity under a single phase, you combine them using this into the 0 0 and 1 0 states. All right. Again, the dimensionality also increases accordingly. Here is 2 and the dimensionality here is 2. So dimensionality becomes 2 times 2, which is 4. So you have 4 possible states, out of which there are 2 coefficients here. And when you apply a C0 with qubit 1 as control here, you end up with this special state 0 0 plus 1 1. And what does this mean? This means that when you measure the first qubit alone, the measurements can still be done separately, but when you measure the first qubit alone and you get a 0, the other will be a 0. Whereas if you measure it as a 1, the other will always be a 1. Like I said, it's very highly correlated behavior, and this is the maximally entangled state. It is making the other qubit completely deterministic when 1 is measured. And this is one of the states called the Bell state. Applying a C0 to this ends up entangling the two perfectly, and you cannot split this vector back like this. You cannot do that. There is a mathematical reason for this. You can read up on it further, but you cannot split it back into these states. This is how it exists now and are dependent on the state of the other. So this is one of the Bell states. The other Bell states you can think of as 0 0 minus 1 1. 0 1 plus 0 1 minus 1 0. Again, all of them capture the deterministic behavior of one qubit with respect to the other qubit. So to sum it all up, we represent this whole ensemble that we've developed with quantum circuits. So quantum circuits are your analogy with your Boolean circuits if you are trying to compare it with a classical point of view. So if you look at quantum circuits, this is a general quantum circuit that I've kept here. You have, as discussed, we've got input states, we've got gates, and each single qubit gate you have here is, you've got Hadamard here, you've got X, and you've got Z, you've got Hadamard again. These are multi-qubit gates. So the dot here, the bold dots here are the targets. These are the controls, and these are the targets, plus symbols here. So these two qubit gates are the entangling gates, the C0 gates. You've got a Hadamard again, and you've got another C. Finally, is the measurement. So some places you can see measurements shown in the middle of the circuit, but since measurements collapse, generally when you draw quantum circuits for theoretical studies as well as when you're actually physically implementing it, you always push measurements to because the measured outputs are then recorded and they're stored into classical registers. You have classical registers that store as memory computer. They do store the final measured states into classical registers. However, that being said, there is also plenty of research to transfer states from the quantum computer to a quantum memory device via an algorithm that I mentioned, quantum teleportation. So quantum teleportation is more like a cut and paste with certain ancillary qubits in the middle to help do this, again through the mechanism of entanglement. However, you might think, okay, if I have, say, a classical computer, usually what I can do is I can copy paste I can create 2 copies of the same data that are identical to each other in every possible way. Why can I do that here possibly? The answer is no. You cannot clone your data. And this is completely captured by something called the no cloning theorem. Again, I can't get into too many details of this. It's slightly mathematical. The no cloning theorem is one fundamental aspect of quantum mechanics and quantum computing, which says that you cannot copy paste a state of one qubit from one qubit to another. You can only teleport, you can only move them from one qubit to another. And this is actually used in the framework of gates itself. They call a swap gate. A swap gate is a gate where you can input two qubits and the output will be the same qubits, but their states are swapped, like the name suggests. And some might think, okay, this no cloning theorem is something that limits us. You know, the no cloning theorem is one of the reasons why you can't store data for a quantum computer yet. However, there are also some good sides to it when you look at something like quantum communication. So the unhack of quantum key distribution that I had talked about completely relies on the fact that no cloning theorem even exists. You cannot completely observe the state of a qubit and then copy it on to the state of another qubit. So if you have a quantum channel of communication between two observers and one transfers, let's say Alice and Bob, right? Alice and Bob are trying to send some quantum bit, some qubit from one to the other. If in the middle of this quantum channel, some, interloper comes in and tries to steal this information, right? Not only in the process are they it and collapsing the state and they're destroying the information present, they're not able to read this information because they don't have the classical key either. So they have only a quantum key that they have and they're collapsing the state and they can't measure it. At the same time, if they try to, measure it and then copy the state just after observing it to make sure that these guys are not, aware of the fact that he is snooped in. Because when you measure it, you're destroying, and the other person is aware that the qubit is destroyed. So they know that their key is useless at this point. So when you have the in your network trying to copy it and send it, he cannot do that. He or she will not be able to clone the state and send it across because that is forbidden by the laws of. So these are some of the important quantum algorithms that we have. We seem to be reaching almost towards the end of the session pretty quickly, but I prefer it that way because I haven't really covered everything in a lot of gory detail, because I prefer it if you all would ask some questions so that I can individually, clarify certain points. But just to, look at these are some quantum algorithms. The Deutsch-Josa algorithm and Bernstein-Vazirani algorithm are two algorithms that were the first algorithms developed in 1992 itself to demonstrate quantum advantage over classical algorithms. These were what started it and new to be researched and tried to, sort of benchmark the performance of quantum algorithms, and they're trying to use them to benchmark the performance of algorithms and to, classify them into certain quantum complexity classes like BQP and etc. etc. So you've got Deutsch-Josa and Bernstein. You've got Simon's algorithm, which came up a little later to solve something called Simon's problem. And this algorithm shows an exponential speed up of quantum algorithms over classical algorithms, which is hugely important because exponential speed up, if it's possible, it is the difference between executing an algorithm over a period of days to mere seconds, right? And all of you might have heard of this quantum supremacy that's been floating around. All of this is based on this exponential speed up that quantum algorithms provides over classical algorithms, and this is demonstrated by Simon's algorithm here. Shor's algorithm is very popular science, in the sense that it was what popularized quantum computation and quantum information capabilities to the world. And this is completely because of its ability to speed up and tractably crack. And it is practically possible to crack the current crypto system, which relies on prime factorization problem. So when you've got your current crypto systems, they work on something called one-way functions. One-way functions are essentially, you've got your data, you perform some sort of a transformation or you apply it to a function, and it outputs something else. Now, the data to this encrypted data, the implementation of that is easy. It's really, for example, it's very easy to multiply two very large numbers with current day computers. However, it's very difficult and much more difficult to factorize these two primes back into their individual primes. So you cannot factorize large numbers back into individual primes very, very easily. It's extremely hard to do even with current day supercomputers per se. And this is one, and the other one is the discrete logarithm algorithm. And there are other methods, quantum algorithms that after Shor's algorithm, that show that not only can they crack these problems, they can also crack other state-of-the-art crypto systems like the elliptic curve crypto systems and the DIS. And all of these things can be cracked practically using quantum computers. So people are trying their hardest to work on something called post-quantum cryptography and quantum cryptography. And quantum cryptography involves QKD, which I had mentioned, while post-quantum cryptography, you still need to send the classical key, which I had mentioned, which is for encrypting your data. So to send the classical key on a classical channel, you need a classical algorithm that is immune in a way and is even on quantum algorithms, and that itself is a separate area of research in quantum and post-quantum cryptography. That being said, this Shor's algorithm isn't, term in its implementation. It's not something that can be implemented today or tomorrow. It will take a while in the current sense of how development of computers is, but it is one of the key algorithms that people are relying on to show that quantum computers are important in the sense that they are so much more algorithms in this sense. Lastly, we have Grover's search algorithm, which is currently the best quantum search algorithm available with slight modifications here and there, which can demonstrate, and it was demonstrated to be the best quantum search algorithm by Love Grover himself in a paper verified by a lot of people. So he not only published the algorithm, he also published why it is the best algorithm out there, and it is mathematically sound. And this demonstrates a quadratic speed up in terms of how fast you can perform a search operation. And this is completely based on this parallelization. You have these quantum states that are in superpositions of these basis states, which represent your strings that you're trying to search for, right? Data as bit strings. So if you have a large enough bit string, a large enough superposition of all of these bit strings, and you can in some way amplify it's called amplitude amplification, in fact, of a particular state to such an extent that you will, when measuring, get that state as the output of the time. Then you can essentially parallelize your entire process and you can perform a search algorithm that's quadratically better than yours available to you. And he's published this in his papers. Again, I'd suggest all of you to, once you read up a little more, get some background, do read research papers about this. Amazing the field is because it's so counterintuitive to our classical logic of going through states one at a time, solving graph problems based on particular node between particular nodes and vertices. All of these are potential candidates to be solved by quantum algorithms. Another algorithm that I missed out on mentioning is algorithm. It's more of a technique, which is called the quantum Fourier transform. Some of you might have done this course called Signals and Systems, which is a course about signal processing, and you know how Fourier transforms are such an important part of your signal processing algorithms and such, where it forms between a time space to a frequency space, right? Here is something along those lines. However, it's more providing your superpositions with a particular phase. And again, this phase is very important because this phase is what gives you your inference-based algorithm techniques. So QFT, quantum Fourier transform, is very heavily used in Shor's algorithm. It's also used in Grover's search algorithm, and it's very, very important technique. Again, I urge all of you to go through these things. I will be providing us a list of references later. So mathematical prerequisites for further exploration. We've come near the end of the session. So here's just some mathematical background for all of you. If you want to go a little further and try to look through this field a little more, because it's honestly so vast. There's quantum information, there's quantum communication, all of these are worth looking through, but similar math background for most of them. So some theoretical background to least would be probability theory and basics of information theory. You can go through a lot of lectures that are available online for information theory, a lot of popular YouTube videos. Probability theory is really important as well. Familiarity with the postulates of quantum mechanics. Like I said, superposition, entanglement, interference, all of these are mechanics. The mathematical background behind it is fairly important because it tells you about these the Schrodinger equation itself and how the solutions of the Schrodinger equation actually behave, which technically explains everything you need to know about a quantum state. You benefit from learning about algorithms and algorithm complexity, basics of algorithms and algorithms. Number theory in cryptography, like I said, for post-quantum cryptography, number theory is a very important component of that. You deal with polynomial rings, fields, very important topics that you could look through later on. Some knowledge of atomic molecular optical physics would be helpful because you want to also try to understand what you're implementing and what the drawbacks and limitations of these are from a physics. So physics is definitely helpful. And you will also understand the limitations with respect to phenomena like noise and decoherence through these subjects. And statistical mechanics, statistics goes very hand in hand with information theory as well. So definitely a plus to learn. Yeah, so these are some of the references that I've followed and that a lot of friends have followed and a lot of seniors and peers have followed. You have IBMQ's blog posts on Medium, and you have by very senior people like Jay Gambetta, who is one of the senior researchers at IBMQ. You've got IBMQ's native quantum programming package called Qiskit. You can look up the documentation at qiskit.org. It's QISKIT. Microsoft as well has these set of tutorials in their programming language and software development kit for quantum computing called QHash or QSharp if you want to, called katas, which are a very, very effective training exercise to understand the nitty-gritty details of achieving certain states using quantum circuits. Very, very helpful. I think they host all of this on their repos and documentations. Professor Umesh Vazirani's video lectures at UC Berkeley are available on YouTube. You can go through those. Those are the theory aspect. So are MIT OpenCourseware lectures by Professor Peter Shor, the guy behind Shor's algorithm. And Vazirani, algorithm was again by Vazirani. So all of these people are actually people who are alive, who are the age of our parents and our grandparents. They're very recent researchers, and it's so new that you can actually, if you progress in your research careers, you can actually go meet these people because it's such a new niche field. You've got quantum computation and quantum information. The best textbook I've seen for quantum computing. It's a textbook that you can find in a lot of online shopping. It's really, really important. It's really useful to understand both the theory side as well as the experimental side of things by Nielsen and Chuang, who are both professors. And last but not least, definitely Professor John Preskill's Caltech lecture notes, which are followed even in the institute.
Need.
Right. Okay. So low temperature physics is in itself a large area of research because low temperature physics is it studies phase transitions and all of these things of at very, very, very low temperatures, and these materials actually exhibit very interesting properties and follow the laws of quantum mechanics. Superconductivity is one very good example of a macroscopic quantum phenomena that exists only at low temperatures, and in fact it is what is used in superconducting qubits by IBM's quantum computers, which require very low temperatures. So these are essentially reliant on phenomena that require lower temperatures to exhibit. Other quantum computers called trapped ion quantum computers. I'll talk about them a lot more detail in a bit more detail rather in the next session that I conduct. Trapped ion quantum computers that go to lower temperatures using something called laser cooling, which essentially traps them in one place. Temperature from a physical standpoint is basically a measure of the degrees of freedom, and the energy of a particular particle or molecule. And if you can constrict these degrees of freedom using lasers, which force them to stay in one place, you're essentially lowering the temperature to millikelvin ranges, or even nanokelvin ranges are possible nowadays. So yeah, that's one of the many reasons are generally used. But you can also have non-low temperature, room temperature qubits, like solid state qubits, because solid state crystals in themselves have very low degrees of freedom. And if you can introduce certain defects in them, like Schottky defects and stuff, certain kinds of defects can act as qubits, and these act as something called spin qubits, which are at the heart of it two-state quantum. Hence, they can act as qubits. So it's not just low temperatures; you can also have solid-state qubits, and they're actually a very healthy area of research as well.
And the second one was, how exactly does quantum computing provide an upper hand with respect to classical computing?
Right. So, I mean, as I had mentioned before, it's not really an upper hand in general. It cannot solve every problem faster than a classical computers, and quantum computers are equal in certain problem in case of certain problems. However, to generalize and say, you can say that any problem that requires a large state space that has a large number of possible states that it can take, and you have a large amount of data, something like machine learning problems, something similar to machine learning problems, you can employ quantum algorithms to provide at least some sort of a speed up in those particular problems. So I wouldn't say that they will compare than classical computers. There are definitely problems where we need classical computers, because quantum computers don't provide a very reasonable advantage. But there are definitely problems which can be solved much faster with quantum computers.
Secondly, what exactly is quantum supremacy and how important is it for us?
Okay, so quantum supremacy, I'm not exactly sure the exact definition. It was actually given by John Preskill himself. It has something to do with the speed up of quantum computers over classical computers in solving a particular task or in computing a particular thing in a matter that is exponentially faster than a classical computer. I wouldn't say that is the way of measuring how a quantum computer is better than a classical computer, since there are a lot of other things that we need to consider. However, it has been popularized because of Google and their studies and experiments with quantum computers. So yeah, I mean, quantum supremacy is one aspect of it, but there are also other things that people have to look at when considering quantum computers.
Okay, do we have any questions from the members of this Google Meet? You can unmute yourself and just fire away.
I'd love to have questions from you guys. Go ahead.
Yeah, there's one in the chat box. Please elaborate C naught gate.
Sorry?
Please elaborate C naught gate in the chat box.
Please abridge. I'm sorry, your audio is not clear.
Please elaborate the C naught gate.
Okay, elaborate on the C naught gate. All right. So the C naught gate, as I said, let me just go back to that slide then. So the C naught gate is a 2-qubit gate. So it operates on the state space of 0, 0, 0, 1, 1, 0, and 1, 1. This is the state space that it operates on, and this is the generalized state vector that it operates on. State it operates on. You've got this gate that basically looks at one of the qubits. It can be either the first one in this position or the second one in this position. And if this is your control qubit, it looks at the state that is in. It looks at whether it's in a 1 or a 0. And what it does is it flips of the one state over here. So let me put it in a better way here. So here I've taken qubit 1 as the target, meaning the target qubit here is the one I'm mentioning, the first one. And since this is the target, look at this qubit. If this qubit is a 0, the coefficients alpha and beta remain the same. And if this qubit is a 1, then it flips the 2. So so you have 1 0 here, it becomes 1 1 here, and you have 1 1 here, it becomes 1 0. So depending on the state of one qubit, whether it's a 0 or a 1, the 0 or a 1 is sort of like a control to the state of the other. So if you have I'm sorry, it's getting a little confused here. Yeah, right. So this is the control qubit here. So since it's a 0 here, alpha and beta remain the same. But since it's a 1 here, the gamma and lambda are switched. Similarly, qubit 2 is the target. So qubit 2 is the target, which would mean that this is the target. So qubit 1 is the one on the left, qubit 2 is the one on the right. If qubit 2 is the target, which is the right qubit, this one, and this is the control, it looks at whether this is a 0. Yeah, if it looks at whether this is a 0, and then it flips beta and lambda instead, since the control qubit here is the one on the right. Is that clear, or should I, probably we can take it up later if you want. Any other questions?
You can unmute the mic and ask the question yourself.
Are there any other questions in the YouTube comments as well?
No, nothing else on YouTube.
All right.
So I guess that's it for today. Thanks a lot, guys, for coming. Thank you, Sashank.
Thank you.
The next session will be on 14th. We'll be using same YouTube and Google Meets for that session as well. Hoping to see you there. Thank you, guys.